know who's on.
So you will have to wear this. First, hand this over to you. No, you should, because that's, I think, how we'll pick up best. Okay. 401. All right, so maybe we should get started. It's my pleasure to. Oh, I can give you one. I will give you. Oh, I don't think we have a remote. So you will have to click.
Have to click?
Yeah. Old-fashioned. So. Yeah, he will get a microphone. That at least we have. Okay, so it's my pleasure to introduce to you Dr. Rene Bellwied from the University of Houston. He received his PhD in Germany, I think Mainz, Gutenberg University in Mainz in 1987, is that right? With a postdoc stint at Stony Brook University. And then, and I didn't know this, he almost came here. And I don't know if you will have time to tell the story, but okay. But instead, he went to Michigan, to Wayne State University, and then did a move to the University of Houston in 2010, where he has been since as faculty. And on the physics side, he has been involved in the high-energy nuclear physics program in the US for a long time. Actually at the AGS first, at Brookhaven, then STAR for more than 20 years now, I guess. And the latest, of course, is ALICE, the experiment at the LHC. And I'm sure he will tell you a lot about that. He has started writing theory papers recently in latticity. And yeah, so he had several leadership positions in STAR and ALICE. And also he has been the chairman of the Texas APS section. When was that, 2019 to 2020? Okay, so Roland's predecessor, that's right. Okay, what else can I tell you? Well, he is actually the first external speaker, colloquium speaker that we welcome back here to our campus. So thank you for showing up here today. And funny story, so your wife was one of the latest, the last ones that we had before the pandemic.
You can ask me whether it's a good idea being married to a physicist.
Okay.
I will not.
Without further ado.
Thank you very much. Thank you for the introduction. Let me see what I can do here now. So, my full screen here. Can I get that? Oh, no. So this is all it. There's an option where. Yeah, what do I do with that? What? Oh, that's good. Like it like that? Okay. Oh. Pants. Thank you very much for the introduction, for the neighborly invitation. I came here. So the story that Reiner started telling you is actually quite interesting, because I didn't notice myself until I drove over here that I was at Texas A&M and I gave a colloquium here almost exactly 30 years ago. I should tell you how old I am. And 30 years ago, there was a job interview for a tenure track assistant professor position. And the talk was good. The interview was good. And I got an offer. I was ready to take that offer, and I would have been here. I would have loved to come to Texas A&M. And the person that I wanted to work with at the time was a senior professor at A&M. And he called me up and said, "You got the offer." And I said, "Great." And he said, "Well, but I'm leaving. I go to Michigan. I got an offer from Michigan." So, and then in the second sentence, he's like, "Do you want to come with me?" So, you know, within a week, my life changed from coming from Stony Brook, wanting to move to Texas. And within a week, I got a job in Michigan rather than in Texas. And I took the job in Michigan. And sometimes you think back at those things and you say, how would my life have been different if I would have gone there rather than here? And now 30 years later, I ended up in Texas. I'm very happy being in Texas. I'm now here for 10 years at the University of Houston, and I have a great time. So the story for the young people is be flexible. You know, things can happen on a whim. be ready to go anywhere in your career, and maybe you make life enjoyable wherever you go. So the other part of the story is that 30 years ago, I worked on exactly the same things that I worked on now. And that kind of made me think a little bit about my age, my field, and so on and so on. And what I wanted to talk about today, if the thing moves forward, which it does not. Oh, scroll works. So if you work in a field like relativistic heavy ion, you work in a field that's about 50 years old, only started in the 70s, really, with the onset of accelerator physics. And you were after a particular thing with what at the time when I joined was the discovery of the quark-gluon plasma. So, you know, I joined a field that's 50-year-old 30 years ago. We made the discovery that we looked for almost 20 years ago. So the question is, what do you want to do next? And rather than giving you one of the many, many relativistic heavy ion talks that you must have heard in this auditorium, because you have one of the best groups in the field right here at Texas A&M, with Rene, with Ralph, with Cheminko, with Jeremy on the theory side, with Saskia, Carl, Bob on the experimental side. You have the top people here, and I'm sure since they are shaping your colloquium, you've heard a lot of talks about relativistic heavy ion physics, and I'm shaping my colloquium over at UH, and I've heard a lot of talk about relativistic heavy ion physics. I'm getting a little bit bored with them. So I thought I'd try to show you what a field that is probably 20 years beyond its discovery, what it will try to do next in order to generate some kind of interdisciplinary research that goes beyond the confines of nuclear physics. Oh, good, I got one. So where do we go from here? And one thing that I always remembered is that one of my mentors, when I wrote my PhD, said to me, if you work in the same field of physics, if you're in academics and for your whole career, you work in the same field of physics, you should consider yourself extremely privileged, because fields have a certain lifetime. And it's not clear that what you're doing at the beginning of your career bridges you over to the end of your career. And to some extent, you also don't want to bridge or be bridged over to the end of the career, because you might feel privileged, but you also feel a little underutilized. And that's my point in the talk today. I want to talk to you about some things that happened in the field that are a little bit more speculative, that could reach into the future, and that don't probably have all the answers yet. And I start, or I end each chapter with questions rather than with answers to those questions. And it's research that's going on right now. And one of the reasons that I got interested in that is that when you look at UH over the last 10 years, we had historically a very, very strong condensed matter group in color superconductivity, not color, in superconductivity. You know, Texas Center for Superconductivity has its own building, very strong group, good people. And then the high energy nuclear people came in one after the other. And right now, these two groups are balanced with respect to what you can actually achieve in terms of faculty, in terms of how many people working on it, how much funding comes in. Everything is kind of balanced, but that leads to kind of sometimes a not so balanced competition, fighting over new positions and stuff like that. And at some point we got together and we said, shouldn't there be some commonalities between matter in completely different parts of phase space, but under extreme conditions, if you want, and shouldn't they have something in common? Shouldn't there be a universality? And what you're looking at, there's a very famous plot from our field, which is the fluid imperfections measured as the amount of viscosity that you get in a fluid. And we found out that the quark-gluon plasma behaves like a near perfect fluid. So it's at the famous string theory limit here. And it's kind of similar in its behavior to superfluid helium or even ultra cold atoms, which are 12 orders of magnitude away in temperature, or 20 orders of magnitude away in temperature when you look at the scale. So you go from 10 to the 12 Kelvin, which is the temperature that we reach, to 10 to the -7 Kelvin, which you see over here in the ultra cold atoms. And the question becomes, is there a universal behavior rather independent of any thermodynamic quantities. And that's kind of what brought us together, and we're working together with the superconductivity people now on things that we think could be quite interesting, maybe revolutionary with respect to quantum computing. And I show you one of these projects as part of this. So I chose 3 projects. I hope I get through all of them. All together, we have I have 45 slides, so you can always follow me here. And if I run out of time, just leave or give me some sign that I should stop or something like that. And I want to talk about all these 3: the quantum collectivity in our field, then quantum states for quantum computing, and our link to nuclear astrophysics. So linking gravitational waves to relativistic heavy ion collision. So these topics are being addressed as we speak. So the data are new, interpretation is ongoing. In the last field here, for example, you have a lot of input also from A&M with Jeremy and Ralph working on things with us. And not all answers are given, but a lot of questions are being asked. And I think that's what's interesting about physics. So before we dive into those, let me give you the highlight reel of relativistic heavy ion physics in 10 slides. Each slide is a highlight. So the first one is the discovery of the deconfined phase itself. You're heating up the gas of hadrons at some temperature. There's a phase transition into a quark-gluon plasma. And this phase transition line, which is a simple TP diagram, right? Temperature versus pressure. Pressure here shown as the density of baryons effectively. If you look at this, there's a phase transition line. This is a picture that we like to draw where we put no numbers on. So you know nothing about it. I could be anywhere. It's in temperature and pressure space. But we know now we know this really well. It's about 155 mega electron volts, which is about a few times 10 to the 12 Kelvin, if you want in temperature. And we know this one pretty well, which is the density of matter inside a neutron star, you know? Few times nuclear matter density, let's say. And there's this phase diagram, and there's this phase transition line, which is postulated. And this phase has been found as of 15 years ago at the LHC and at RHIC. And what I show you here in shades are the different areas covered with different energies that you can either have in an accelerator or energies that you could potentially have in neutron star mergers and in neutron stars themselves, in cold neutron stars. So the interesting thing about this curve here is that we always had these 2 lines here: highest energy at RHIC, highest energy at the LHC, what you can achieve in terms of initial temperature and density. And then we lowered the energy at RHIC, and the density goes up, but the temperature goes down. But then even more dramatically, over the last 5 to 10 years, we made links to nuclear astrophysics. And this started really with the gravitational wave measurements of neutron star mergers, which we postulate now covers a regime in this phase diagram, which can be potentially linked to the lowest energy regime at the relativistic heavy ion collider at Brookhaven, or new machines in Germany or in Russia. So there's Nika in Russia, FEA in Germany, and RHIC is running fixed target experiments now, not in collider mode, reaching down into energies that are very similar to what we can simulate happens when a neutron star sees another neutron star merger. So we're making links in terms of density and temperature to other fields. The story over the last 15 years went first with the discovery of the quark-gluon plasma, which turned out not to be a plasma, but turned out to be having liquid behavior, collective behavior, almost perfect liquidity, which is best described by this eta over S plot, this viscosity over entropy plot, which we then renamed to fluid imperfections in order to compare to other things that you're more familiar with. And you see at very different temperature scales, they behave, something at 10 to the 12 Kelvin behaves like superfluid helium, almost, even better, right? That's the point. Maybe even an order of magnitude better. So it's a perfect liquid. It's not a gas or a plasma. That made the AIP science story of 2006, head of Scientific American, headline Scientific American. The next thing we did, which I thought was very interesting, and I'm much more interested in the creation of matter, if you want, through this process, rather than characterizing the plasma phase itself. If you're interested in the creation of matter, the next thing we made is antimatter. And that's a big deal because we tried to find antimatter in the universe. We sent satellites up there. We still don't have proof from the satellite experiment. I would say we don't have unambiguous proof, but we made it. So this is different than antiparticles. We took antiprotons and antineutrons and we made an anti-helium molecule. And if you look at what we did on the antimatter side, antiproton, antideuterium, anti-helium-3, anti-helium-4, and you look at how the yields fall off, they fall off exactly the same way on the antimatter side than on the matter side. So at this point, you can start to extrapolate how much energy you need to make anti-lithium, to make anti-beryllium, but there's nothing in the way of antimatter creation that is any different than on the side of matter creation. So if you would leave the antimatter alone, you would get an anti-universe. And that's something to ponder over, you know, because we're living in a universe, but not an anti-universe. But antimatter behaves just like matter. That was science story 5 years later, 2011. And then when you are in a field like mine, you don't get many nature articles, you don't get many science articles. So anything that makes it into science and nature is big. So the next big thing is that you're essentially generating with these very high energies a strange matter factory. And the first thing we measured was strange antimatter. So I showed you helium-4, anti-helium-4. Here I show you antimatter that has strange particles in it. So an anti-hypernucleus. Instead of an anti-triton that you see here, you're replacing one of the neutrons with a lambda particle, and you get an anti-hypertriton. And that works too. It's there, the peak is there, the lifetime works. So strange quarks can replace light quarks in basic nuclei and generate metastable matter. And we make plenty of it because we are at very high energies. And these are energies few microseconds after the Big Bang. We have to recognize that these are processes that in this way could go on or could have gone on in the universe along the way. Next thing we measured is that when you have a very non-head-on, now I lost it. If you have a very non-head-on collision, so one of the nuclei comes from the one side, the other one comes from the other side, and they hit each other, but they don't hit each other head-on, they start rotating. The middle, the interesting phase here that you're generating in the middle where they collide with each other starts rotating like crazy. In other words, a huge amount of angular momentum. That huge amount of angular momentum turns into a huge magnetic field, largest magnetic field ever measured. That's when you compare this to magnetars, which are stars that do on the order of 10 to the 15 Gauss as their main magnetic field. This is about 4 orders of magnitude higher. So you can reach up to 10 to the 19 Gauss. So you have a magneton, and that magneton generates interesting effects in the soup that you're making. It generates vortices, and these vorticities can be measured. And this led to the Nature paper here that's called Subatomic Swirls. The problem with it is that the lifetime of this field is extremely short. So you can't see that, I'm sorry, but this is 1 Fermi over C, so 10 to the minus 23 seconds or so. So what you see here is that the field falls off so fast that these vorticities live for a very, very short amount of time. But then you can ask yourself how they impact the debris that comes out of this interaction. And that is generally true for anything we do in relativistic heavy ions. The plasma, the liquid that we're making, lives for about 10 to the minus 22 seconds. You will never measure it directly. You will never put a probe in there and say, okay, what happens? The only thing that you have is sifting through the debris and understanding the debris, and from the debris, learning something about what has happened 10 to the minus 22 seconds ago. And one of the things that has apparently happened is huge vorticities in this liquid. Next thing is an enhancement in strange particles. And this was one of the early signatures of the quark-gluon plasma. And I actually glanced over this in my first slide. I showed you the things that showed us that we had a liquid, because I think you've heard about this over the last 15 years. So I'm not going to roll it up anymore. We have the plasma. Let's talk about what we can learn from the plasma. But one thing that we will always show, and the thing that is important to the 3 topics that I want to show you today, is that we have an overproduction of particles that contain strange quarks. The whole world made out of up and down quarks, If you make a strange quark, you make the next heavier quark, and these particles that have that next heavier quark are overproduced in this interaction that happens a few microseconds after the Big Bang. Furthermore, and this is one of our papers here, we have shown that they actually freeze out, they come out of the plasma at a higher temperature than particles that don't have strange quarks. By about 20 MeV, but that might be an interesting point because for 20 MeV, the strange matter in the universe is by itself. And if it's by itself, it could probably cluster, it could conglomerate into certain strange particles that we don't see right now flying around freely, but they could be in some dense stellar objects, for example, and that's one of the points that I come to at the end. That's 2017, you see we're going forward in time. Here's the last one, which relates very closely to the one that I just showed you, which just came out this year, which is the idea that strange baryons, baryons with a strange quark in them, so lambda particles, for example, have an attractive potential to non-strange baryons. And if they have an attractive potential, and I'm not going to go into the details of these calculations, it shows that the interaction between these particles and non-strange baryons is attractive. If they have that attraction, they can form multi-quark states. So there's a doorway into hexaquark states, pentaquark states, tetraquark states. And some of them were found already by the LHC in the charm sector, so when charm quarks are involved, but we haven't seen them yet in the strange sector. This calculation, though, shows A, that they should be possible in the strange sector, and B, it shows that the interaction between the strange and the non-strange baryons is attractive, and that becomes extremely important for the equation of state in dense stellar objects, neutron stars, or even black holes, where this could become the ground state of matter. And that's something that we're looking at. So topic number one. So I'm going to go through those. If you get bored, let me know, raise your hand, I move on to the next one. So topic one is quantum collectivity. And it goes back to the fact that when we describe certain things, we get a good understanding of a particular aspect of it, but we're not getting a really good understanding of everything. And the question is really, why don't we have really a quantum mechanical description of what's going on in a heavy ion collision? We don't have it because it's extremely difficult. It's a many-body quantum problem that you're trying to solve with the quantum field theory. And you probably have encountered that in your classes when you teach QFT versus QMB, that there is not really an interesting or an easy connection between the two. And one example is we have the Higgs field now. We measured the Higgs boson. We know that the Higgs boson gives mass to the quarks, but it gives different mass to 6 different quarks over 6 orders of magnitude. And we don't understand why. The only way we can do this is we give each of these quarks a different coupling strength to the field. That's what a mathematician would do. That's not what a physicist would do. Physicists would do, why is there 6 orders of magnitude difference in the coupling between these? So we don't really have a good understanding of mass generation. And that goes on and on and on. If you go to the idea of the mass of the proton compared to the mass of the quarks that make that proton, there's a huge discrepancy of, 915 MeV is missing, right? That the 3 quarks make up very little of the mass of the proton, but then we call it QCD mass, and we can calculate it. And I will show you that lattice QCD does very well. So if you have a Lagrangian on a lattice and you put an action onto that lattice, you can actually calculate these masses quite well. But a deep understanding of how that action really propagates from quark to quark is still missing. So that is described in the phase transition with 2 things. It's described with the chiral symmetry restoration, and it's described with confinement. Those are the 2 things that you learn in QCD effectively as the 2 things that should happen during a phase transition from a hadron to a quark. Neither one of them is really well described in a fundamental way, in a quantum mechanical way, I would say. And so I'm sounding like one of my Russian friends who says, confinement, what is this? I don't understand it, So maybe I don't understand it either after working on it for 30 years. So let's see whether we can learn a little bit more about it. Here is the success of lattice QCD. I don't have a citation on it, I'm sorry, but this came out probably 2005 or something like that, calculating the masses of all the known baryons at 0 temperature. And you see, if you input the masses of the lowest mesons, the pions and the kaons, you can predict all the other masses to almost perfect accuracy on the lattice. So the interaction of quarks and gluons can be described with a Lagrangian, a QCD Lagrangian on the lattice, and it describes the masses of the particles. So we know that this mass that is not given in the free quarks comes through the interaction with the gluon fields, and it adds up to the right mass. One thing that is not so satisfactory is that it has to be anchored. It has to be normalized at a mass, namely the pion mass, otherwise it doesn't work. And the other one is not so satisfactory, that it's at 0 temperature. So nothing is at 0 temperature. And you actually making now experiments that are at 10 to the 12 Kelvin. So you probably would like to see how this looks at non-zero temperature. And what lattice QCD can show you is that all the quantum numbers that you know, isospin, charge, up and strange quark susceptibility, and baryon number, goes through a phase transition at a particular temperature. And this is the famous pseudo-critical temperature we now quote as the phase transition temperature. You see, it's not a first order phase transition. It's not even a second order phase transition. It's a crossover. It's an analytic crossover, but it happens at about the same temperature for all the different susceptibilities, for all the different quantum numbers. But the difference, for example, that I showed you of 20 MeV between strange quarks and light quarks comes right from this picture, right? There's a 20 MeV difference between what the S is doing and what the U is doing on this picture, if you fit lines to it and calculate it out. So it always happens in a range, but in that range of temperatures, the transition is kind of not well defined, and a lot of interesting physics is going on. And a lot of this physics you would like to understand better. You would like to see whether you can show what a particular quantum number connected to a particular particle is actually doing in that part of space. The big success of particle production that was touted a lot in our field is that if you forget about the dynamics and you calculate the yield of all particles that are produced coming from a simple thermal source at a fixed temperature, it describes the data quite well. So this is very simple physics. This is essentially statistical thermodynamics applied to particle production. And the interesting thing about the particle production is, it turned off. The interesting thing about the particle production is that it covers particles over 9 orders of magnitude. It covers particles from the pion at a yield of about 1,000 per event to anti-helium-4 at a yield of 10 to the minus 6 per event. And it does really well. This is data over model with a statistical model. A statistical model that simply says all of these particles were frozen out from the quark gluon liquid at a fixed temperature of 156 MeV. I showed you that if you go into the details, and 9 orders of magnitude sometimes can hide the details. If you go into the details of that, you found that the strange and the light quarks do not freeze out at exactly the same temperature. But if you glance over it, like in a common way, what you see is that it works quite well. And this was a Nature article just recently that showed that this is our picture. Now, one thing that you should immediately notice is that a particle like a deuteron or a helium-4 particle that has a binding energy on the keV level freezes out perfectly fine out of a heat bath at 156 MeV temperature. How can that be? Why doesn't that thing get immediately dissolved when it's in that heat bath? How can it be that that particle comes out with the exact right yield out of a heat bath that's a factor 1,000 hotter than its own binding energy? Very puzzling, not understood. There are some ideas, but not understood. And that's one of the things that led me to, I'm coming very slowly to the quantum collectivity thing. That's one of the things that made me wonder of whether this simple idea of a perfectly thermal system developing over time and then just freezing out happily into 9 orders of magnitude of particles is the right picture or not. Because we're talking about a system that is highly violently formed, and then we're describing it with a thermal equilibrium picture. Can that really be? Does it make a lot of sense? And one alternative, and I'm not telling you that that's the right alternative, that's just something that I'm interested in, is the idea that we have forgotten about certain quantum features when we calculate stuff. And one of the easiest quantum features that you can understand that we have forgotten is that when we look at a proton hitting a proton, we don't calculate it like that. What we're calculating is 3 quarks hitting 3 quarks. And even more so, we're calculating 1 quark hitting 1 quark. We're completely ignoring the rest of that. We call that a parton model. Famous event generators like Pythia have that at their basis. So, you know, parton on parton. We forget that that parton is part of a proton. You cannot forget that that parton is part of a proton. The other 2 quarks in that proton will affect its wave function. It will affect the density matrix of states that you can produce in this parton-parton interaction. Completely neglected here. So there's many ways of fixing this, and I don't want to talk about those. This becomes very special. But generally speaking, these models, on average, ignore quantum mechanics. So one of the things you could test is you could say, what if I don't ignore quantum mechanics? And the one thing that you can label this to, and this became very popular over the last few years too, is quantum entanglement, which brings me from this topic right into the next topic. But here for this topic itself, it simply means that that quark that's interacting out of the proton is entangled to the other 2 quarks. And then furthermore, after the interaction, it's also entangled to the quark that it interacts with. So there's an entanglement in longitudinal direction and an entanglement in transverse direction, which gives you a volume entanglement, at which point you can take an entanglement entropy and you can probably, just bear with me, crazy old man talking, you know, equating it to thermodynamic entropy and calculating whether that could have an effect like thermalization, although the system is not thermalized at all. And the one guy that you want to refer to is Schrödinger, who said it's crazy to do an experiment and thinking about that a particle that's clearly not isolated and thinking about it as an isolated case that tells you something about the physics. A quark is never isolated. A quark will always be entangled with other quarks, and it has to be taken into account. Can I prove this? Now, before I prove it, let me tell you why this became interesting as of late, which is 2 experiments, again, in a completely different field, in a completely different part of the temperature scale, of the pressure scale, namely first ultra cold atoms and then a little hotter. What they found is that if you take a system, ultra cold atoms, and you perturb it, that perturbation will transport around the quantum entangled states. And after a certain time, it will look like as if these states are thermalized, as if they carry the same amount of energy. And the only reason that they do that is because they're entangled. And the first guys who found that were the Harvard group from Kaufman. Very interesting experiment and relates directly to what I'm talking about. In this case, it's a Bose-Einstein condensate of rubidium atoms. And I venture to say that it behaves almost exactly like a quark-gluon plasma. So there you see the link between those. Now, entanglement in this case goes very, very short, goes to neighboring atoms. And people will always tell you, if you apply this to a many body systems like many quarks, don't do that, because as soon as there are interactions between the quark, the coherence will be broken. You will get decoherence. When you get decoherence, the entanglement is gone. And that was kind of frustrating until the Kong paper came out in 2020, which says that they found this not only in a cold system, but in a hot system of strongly interacting atomic systems. And they found it over thousands of times of the nearest neighbor distance. That means thousands of atoms that were entangled carried that coherence through the interaction phase, through the strongly interacting phase, and kept it. So that's kind of encouraging, because that goes in the direction of a quark-gluon plasma. And if you believe this and you want to apply it to proton-proton interaction, you want to apply it to proton-proton first before you apply it to heavy ions, you can try to make a simple test. And the simple test we did first on CMS, on the CMS experiment. We're now doing it also. And in ALICE, what you need is so-called forward coverage. So you need coverage at low angles to measure a lot of momentum transfer. So what I'm plotting here is entropy versus momentum transfer. So the more momentum is transferred, the deeper you go into your distribution function, the more forward you have to make your measurement, so at small angles. And what you see here is what you would get from a parton model like Pythia, and what you would get if the entanglement entropy is equal to the thermodynamic entropy. So you would get an effect that when the gluon distribution density goes up, when you get more and more particles deep in the proton, the entropy should go up. And when the entropy should go up, the charge particle multiplicity should go up, the number of particles that you measure. And here's the data, different coverage of angles, 0.5, 1, 2. I'm not explaining what pseudo-rapidity is here. You can read a little bit about it. The data seem to just qualitatively have a trend. They're not flat. And as soon as they have a trend, it is not something that a parton-parton model at this point can describe. It's something that you want to look at. It's a simple experiment. You just measure the number of charged particles. And if the charged particle multiplicity really has this very strong dependence on the fractional momentum, then that's a signature of entanglement. So this is the first experiment of many. We will go further with this, but this is one of the ideas. So I leave you with 2 questions, or 3, rather than answers. Is the collectivity in a deconfined phase due to actual thermal equilibration, or is it due to quantum entanglement? It's very different. An entangled system is not equilibrated ever, right? It's entangled, but it will not equilibrate. Which scale is relevant, the quark scale or the hadronic scale? And does the entanglement in the initial state determine the particle multiplicities in the final state? When I listed the papers in the beginning, you saw I wrote one of this. The one that I wrote is the most ridiculous one, because I said that will not only be there in proton-proton, but it could potentially survive all the multi-particle interactions in lead-lead collisions, in heavy ion collisions, and potentially lead to an entanglement effect in heavy ion collisions. The answer, we will have to wait for probably. The second topic my first topic kind of leads into the second one, which is quantum states. And here is a very famous old simulation from Lineweaver and Company in Australia, where they show the cooling of the energy density of the QCD vacuum early on in the evolution of the universe. So what you see is that the energy density fluctuates, and the energy density forms kind of blobs of particular density. That energy density blobs can be translated into topological fluctuations. That means you can generate topological charges, and here the gluon field can generate these topological charges, and these topological charges, the fluctuation of these topological charges could potentially lead to an effect which is called the chiral anomaly. Now, this is pretty heavy stuff, and I'm an experimentalist, so I refer you first to the Nobel Prize on this, which was 6 years ago, topological phase transitions and topological phases of matter, given the Nobel Prize in 2016. And the idea I will try to describe very briefly, but it is a little bit important that you kind of know what a skyrmion or instanton is in order to understand it. But generally speaking, what you have is that a topological quantum number is any quantity that takes on a discrete set of values under topological consideration. So the question is, what is a topological consideration? A topological consideration is that under certain symmetry operations, for example, SO2, you will have a fluctuation which comes from the fact that the system is isomorphic, and isomorphism is a topological group. So it's generating a fluctuating field. And that fluctuating field will have an impact on the charge, and the charge does not have to be charged. It could be baryon number, it could be isospin, it could be any quantum number. It will generate a field that has an impact on the orientation of these quantum numbers. Yeah? So what these charges do in particular for us, which is important, is they generate an actual anomaly. That means we call it the Cardiomagnetic Effect. And you might have heard there was a press conference about it just 2 weeks ago. So I show you what the press conference was about. But effectively what you have is and I show you this in the next plot. If you have a system with fermions, with chiral fermions, then depending on how they interact in the topological landscape, they will orient themselves in different directions. That means the spin of the system will orient itself in particular direction. And that spin of the system can then effectively be used if you have a strong magnetic field in the system. And remember, we have the biggest magnetic field ever, 10 to the 19 Gauss for a very, very short amount of time. So if we can orient those spins with our magnetic field that we generated through the actual anomaly, then we can probably generate this imbalance. And this imbalance is nothing else than an up-down state effectively. You can get from one spin state to the other spin state. You can flip it. And you see already where this is going. If I have a quantum number that I can flip 0, 1, 1, 0, 0, 1, I can probably use that in as much as I use a 0, 1 scheme in a normal computer. I can use it probably in a quantum computer. So here's the general idea. So you have a number of quarks and antiquarks. They have an orientation. Chirality is nothing else than helicity. So it's really speaking the orientation of the spin with respect to the momentum. So they could be aligned or anti-aligned. And these aligned or anti-aligned, right-handed or left-handed quarks, if you want, are then being put in a magnetic field. And if they be put in a magnetic field, and the magnetic field here is generated through this huge rotation of the quark-gluon plasma, you effectively get a separation of charges. And the easiest charge to look at would be the electric charge. So rather than looking for baryon number separation, although Chiming has a good idea with baryon number, you look for electric charge. You see whether the plus and the minus particles go into the different parts of the hemisphere relative to the reaction plane. And that was the measurement. Yeah? And we got very excited about this in the quark-gluon plasma because of the strong magnetic field. In the quark-gluon plasma, we also found a result that looked very exciting, which is the separation. And the more and more you go non-head-on with your collision, so we call that centrality, the more you go away from central collisions to peripheral collisions, the effect of positive versus negative charges splits up more and more. You see more and more positive or negative charges. Now, one should be careful. It's a heavy ion experiment. Positive and negative charges are being pushed through many, many different effects in a heavy ion collision. Flow comes to mind, collectivity, everything pushes in different directions. That means all of these simple effects have to be subtracted before you can make a point that you found a chiral magnetic effect in heavy ion collisions. And the years went on, and one has to say that physicists are honest, right? That's one of the things that we are. We try to, we're trying not to let politics tell us what to say and what not to say. So we haven't found physics beyond the standard model at the LHC, and we seemingly haven't found the chiral magnetic effect at Brookhaven. So here, with years, the data became kind of a little bit better defined. The subtraction of the background became better and better. And this is what we found and showed at the last Quark Matter conference, which shows that the effect, if it's there at all, is on the order of 10% at most. 10% plus minus 10%. So at that point, the laboratory said, we give you a dedicated run. And it's an interesting thing just from a physics point of view to see how this came about. We give you a run of 2 isobars. We let you run rubidium on rubidium and zirconium on zirconium. And the difference between those 2 systems is that their isobars, the one has 4 protons more than the other one. 4 protons more is exactly 10% more protons. 4 protons more gives you a stronger magnetic field. The field is larger in the isobar with the more protons. So you make an experiment. And this was what happened on September 1st, big press conference. But the lab also said, we don't really trust you because we know that you want to find something. So in order for you to do it like you would normally do it, we want you to do it with a blind analysis. Blind analysis is that 5 groups get the same data. Nobody knows whether they got zirconium or zirconium or rubidium or rubidium. They all analyze, they calculate, and then you compare the data. And this is the result. This is a massive undertaking. And this is the result, without going into detail what each of these measurements means. This is the result from all 5 groups. And what you should have seen here is a level at about 1.1 in order to see a chiral magnetic effect. So this announcement was that we didn't see the chiral magnetic effect. The chiral magnetic effect is not there at this point in heavy ion collisions. It was postulated. We saw some intriguing evidence in 2015. We don't see it right now. So it could be that the field is even stronger, not necessarily stronger, but has a longer lifetime. If you go to lower energies, the magnetic field might live longer. And there is a remote possibility that you see more at the lower energies. But at this point in time, we don't see it. So you might ask, why did you even talk about it? I talked about it because at the same time, and this links us to our condensed matter group, that effect is there for any chiral fermion. And a quark and a gluon are not the only chiral fermions that can fly around in the system. And Weil and Dirac independently defined a particular group of metals that could have chiral fermions, and then they call them semi-metals. And without going into the details of this, we have a group, and we worked with them at Brookhaven. So our condensed matter group worked with the condensed matter group at Brookhaven, who worked with the relativistic heavy ion theorists in Stony Brook, who worked with us, and they indeed found one of these metals, which is zirconium telluride. And if you look at zirconium telluride, there is evidence for a chiral-magnetic effect in zirconium telluride. There was a Nature Physics paper in 2016, and since then, this part of physics has gone quite a ways. So without going into the details, you see the effect, and you can control this effect, and you can control this effect by putting polarized light on the system. So the polarized light in the magnetic field in which you put the semi-metal leads to the fact that you can effectively choose which of those two states will be populated, the 0 or the 1 state. And that is very much like you use a superconducting metal right now in the qubits that exist already. So this is the Intel qubit at low temperature based on superconducting material. And this would be a possible idea of using this not at super cold temperatures with a semi-metal where you can use polarized light in order to switch them rather than switching them in a superconducting magnet. So, you know, if you want more information, go in it. I'm just touching on these things in order to show you how the field generated new fields. So what we have is cardiomagnetic effect. Can it generate topological charges that can be used as quantum states of qubits in quantum computers? Question I leave for you, and I think many of you will probably work on this at some point in your career. So my last topic, 5, 10 minutes, 10 minutes, what? Yeah. Thank you. Then I move on to interdisciplinary astrophysics. Pretty excited about this because it's something that came out of gravitational wave measurements. And I don't know how you felt about gravitational waves. I mean, when they came out, I think I was very excited. Like, oh, didn't know LIGO could do that, right? I mean, I was in Michigan when University of Michigan suggested LIGO was one of the lead institutions, and I had a lot of discussions with them, and I was like, yeah, that's a nice experiment. If the government has money to waste, let's build LIGO, right? I mean, this looked like so improbable. This looked like so crazy an idea that I was like, man, whatever, you know? And then they measured it, and I was so excited. I was so happy that fundamental research can lead to such a breakthrough. But then 2 days later, I was like, okay, we found, so what do we do with it? What's so interesting about it? And then my astrophysics friends kind of educated me really well. And I'm very happy about this because this is really, really interesting. And it links to what I showed you in the beginning, that our phase transition plot now reaches down to neutron stars, and it reaches down to neutron star mergers, and the energy of a neutron star merger and the gravitational wave that it generates tells you something about the phase transition behavior in my first phase diagram, and we can learn from them. So one of the big questions is whether we can determine the equation of state of the core of the neutron stars. And this was always, for the longest time, a question of, can a neutron star really exclusively be made out of nucleons, out of neutrons and protons? You know, so that would be your nucleon star, your standard star. Then it could be a neutron star with a pion condensate. It could be a quark hybrid star. It could be a star made out of neutrons and lambdas, like I just showed you. I can take the lambda out, the neutron out, and make a hypermatter. It could be a hyperon star. It could be a strange star. It could be all of them. So there must be a difference in the behavior of this star based on what's in the core of it. And we always like the neutron stars as relativistic heavy ion people because we firmly believe that there's a plasma in the core of this star. So we really wanted to try it. And the difference between all of this is the equation of state, what you put into the equation of state. And there is lots of new programs going on. Ralph has joined one of them together with Jeremy. NSF funded, where they bring together nuclear physicists with astrophysicists, gravitational wave people with relativistic heavy ion people, trying to understand what's going on. And I think that's a very exciting time. And how does it relate to what we're doing? Mostly with the three discoveries that I showed you, which relate to strangeness, namely strangeness enhancement as a function of number of strange quarks in a particle, the generation of hypermatter, and the attractive potential between the strange particles and the non-strange nucleons inside the neutron star. So there's an attraction between a lambda and a neutron. If there's an attraction between a lambda and a neutron, it should lead either to hypermatter or to dissolution into a multi-quark state. And depending on which way it goes, it has a different impact. And if we believe in the thermalization of the picture, we can actually calculate what kind of crazy hypernuclei we can make and how many we can make at the LHC. And if all of these now predictions would come true, you know that you have a thermal model that could describe the core of what's going on in a star that is made almost exclusively out of baryons, strange and non-strange baryons. So the idea is, and it already shows in these calculations by the Frankfurt and the Kent group, is that when you try to simulate in particular, and you have to distinguish now in gravitational wave measurements between black hole mergers, two black holes finding each other, and neutron star mergers, two neutron stars, and a neutron star black hole merger. And at some point, the difference between a neutron star and a black hole becomes kind of fuzzy. It's mass versus radius. And we're really talking about things that are, 10, 15 miles of radius that are somewhere out there, and we're trying to measure them a few thousand light years away. So it's not trivial by any means, right? But if this was indeed a neutron star merger, then the energy value that you're getting and the temperature that you're getting here, temperature on the order of 30, 40 MeV, the density, the log of the density around 5 to 10 times nuclear matter density, that's exactly what we can generate at an accelerator at RHIC, NICA, and FAIR. So it becomes very interesting, and this is a simulation of a heavy ion collision, which is a simulation of this neutron star merger at the right energies. So the merger will go through, it will look like a heavy ion collision effectively. Now you have to be careful. This is part of this merger phenomenology. It's the in spiral thing. It's the thing when they come together. So you have to distinguish a little bit the different phases, right? The in spiral brings them together, then they merge into each other, and then there's a post merger. And the nice thing is in the gravitational wave, that gives you a certain pattern. So this is a gravitational wave pattern. It's a gravitational wave pattern. To be honest, and we want to be honest physicists, the only thing we have measured is this part. We don't have resolution to measure this part yet. So what LIGO and Virgo can do gives you this, but it doesn't give you this. But there's a lot of stuff going on now after LIGO and Virgo was successful to go beyond this and continue to measure this. And then you have this interesting effect of two different phases in spiral, merger itself, and then the post-merger effectively ringing down, essentially, falling, either becoming a equilibrated cold neutron star or a black hole. What it really becomes depends on the mass and the radius. And here's the interesting part. You can now calculate as a function of the mass of the star, and the mass of the neutron star is always given to you as a multiple of the solar mass. So you know how much the sun weighs, and then you measure a star that is 10 miles in radius that has 1.2 to 1.3 times the mass of a star. How they ring will depend on whether the equation of state that you're using is soft or whether the equation of state that you're using is stiff. And that is something that is driven by the makeup of the inner part of the star. It's driven by the core of the star. Is it quarks? Is it hyperons? Or is it nuclear? And here's a very interesting thing, which hopefully, if you get the resolution to measure it, is predicted. Namely, if it's a hadronic core, it rings down in the black way. If it's a quark core, it rings down in the red way. So it's out of the ringing down, you can make a distinction between whether the star is a quark star or whether the star is a hadron star. And it depends a little bit on the mass again. 2.8 solar masses. We haven't seen something with 2.8 solar masses yet. 2.9, even worse. But you see, the heavier the mass, the more the ring down gets squished away. It kind of, but still you see the difference between with and without the quark phase. So a lot of activity there, a lot of things going on. You can calculate what happens to the quark phase in the system. And one thing you see is that the quark phase in the system at some density and at some temperature, and these temperatures are now considerably lower than what you get in the LHC and RIC. But again, there are at the same temperature range that you can get out of low energy accelerators. At some point, it turns from a crossover into a first order phase transition. And at a low temperature, but at a high density, it turns into a first order phase transition. And again, interesting work. If you want to know more about it, there is a paper for you. So the idea is that depending on what your star has, what core composition your star has, nucleonic matter, hyperonic matter, or quark matter, you can make an equation of state. And the equation of states to first order look not so different as a function of pressure versus density. They look pretty similar, although the quark one completely dies off here, but it looks like, oh, it's difficult to do. But when you then translate it into a mass versus radius diagram, you see huge differences between those. So some equations of state are excluded by certain mass radius ratios. And these mass radius ratios of normal cold neutron stars right now are being measured massively by the NICER experiment, that the satellite experiment that NASA has shot up about 2 years ago. They measured by now almost 2,000 neutron stars. We have a huge number of mass versus radius points on this plot, and I don't show you all of them. I don't show them to you because I want you to see. You know, you can look them up yourself, and you can see. The interesting thing is that a lot of it happens if you get to masses above two solar masses, and that's something that very few neutron stars have at this point. So we have to generate the right statistics. But together with this, and then the other effect that you can measure is the spin, the rotational speed, because these things are swirling like crazy, these neutron stars. Out of the spin, you can also measure what the input, what the core of the stars. So, you know, it's a combination of what you measure phases in an accelerator experiment to what you measure in the sky. So quite interesting, quite exciting. And so I leave you with the last questions here. Do neutron stars have strange quark plasma inside? Is that possible? And can we determine an equation of state through an interplay between relativistic collisions, gravitational waves, and neutron star mass to radius measurements that tell us a lot, not only about neutron stars, but also the thermodynamics of black holes and a lot of things that we don't know much about in the sky, right? We have no idea where 10 to the 19 GeV cosmic ray is coming from. So here's my last slide. The only thing I want to impress on you is that starting off with relativistic heavy ion physics and measuring a deconfined quark gluon plasma suddenly has an impact on condensed matter physics, on basic QCD, you know, on cosmology, on string theory. I didn't touch string theory. It kind of fell out of fashion as of late. You know, let's find some beyond the standard model physics, and then I start talking about it again. But the other three are really very much impacted right now by what we're measuring. And it's a nice symbiosis between experiment and theory in both fields, in astrophysics, in nuclear physics, in condensed matter physics, in nuclear physics, in high energy QCD, in nuclear physics. And I think this is very exciting. And it gives you many, many avenues to work on with an experiment that really was just meant to find the quark gluon plasma. And it does much more than that. Thank you very much. Okay.
Oh,
Can you hear us on Zoom?
yeah.
Okay, good.
Mm,
Oh, let me go back to the slide. Yes, so the question was about the freeze out temperature, of molecules, let's say any molecule if you want, with a small binding energy in relativistic heavy ion collisions, and what's the statistics and what is the accuracy, I would say, with which it's measured. The statistics is really given by the error bar that you see here. So ultimately, we measure these particles, I think for helium-4, for anti-helium-4, you mean, or for helium. For anti-helium-4, we have about close to 100 over the period of the time we measured. So we started off with 10 to 15, that's what we wrote the paper. But then we accumulate, right? We accumulate more. We have about 100 of those. Now, clearly that measurement has the largest error bar, right? And also has the largest error bar in the comparison to the model. But if you change the model by more than 10 MeV, let's say, you will not be able to describe the yield. So my point is not so much the absolute value of 156 MeV. My point is the factor 1,000 difference between the binding energy and that temperature. So the system is really a very loosely bound system in a very hot bath. And you know, so there is an idea that it's formed early. It breaks up, it dissociates, it comes back together, it breaks up, it dissociates, comes back together, dissociates, and slowly cools down. And then at the last step, you have a coalescence, which then reflects the exact same yield that it had when it was produced, because the two partners always find each other. But it is very, very, if you think about it, it's very unlikely in a heavy ion collision, because there are hundreds of protons and neutrons. Why would it always recombine with the right neutron to make exactly the yield that it had? So we don't have a good explanation. There is a paper, an early paper by Kapusta and Chernai and Kapusta, who said essentially it's what fixes in is the entropy over baryon ratio indices. And therefore, you know, if you freeze the entropy, you therefore freeze the number of baryons, and therefore this number of baryons, no matter what the baryon is, cannot change anymore. And then a helium-4 is just treated as a baryon equals 2 instead of baryon equals 1 quantum number. It's not really an explanation. It's something that but there are, let me say that there are ideas out there. I didn't talk about them today because I wanted to just give you the facts, and then you can think about it. But that's the fact. The fact is it has about 130 keV binding energy, and it's in 150 MeV bath, and it doesn't seem to be much affected.
Oh. Hello, may I ask a question?
Wait, Ralph is still, we're having a discussion in the room. Give us 1 second. it's still a high temperature. I mean, it's a breakup temperature. It's yeah. So that's what I mean. I mean, that there are definitely ideas. The one that I wanted to show was quantum entanglement because it's fancy. It's flashier. Go ahead. The question from the Zoom.
Valerie, ask your question.
Yeah.
Go ahead.
I have two questions. The first is, what is the nature of strange particle interaction? Attraction, sorry. Is it known what is the nature? And the second question, what oscillates in the neutron stars merging processes?
The first question is, what's the attraction of?
What is the nature of attraction of strange particles? Why this, which is probably responsible for this generation of strange particles?
Yes, let me go back to the plot if I can find it. Well, actually, I want to go back. So this thing is confusing. Here. What you can see on the plot here is different calculations of the interaction potential that you have when you have, in this case, protons acting with omegas on the lower one and protons acting with cascade particles on the upper one. And what we can compare is the first thing you have to take care of is that it's a proton charged particle interaction. So you have to subtract the Coulomb effect. You're subtracting the Coulomb effect, and you see the Coulomb effect here is in green, but it does not describe the attraction that you have. So this would be an attractive form because it's a positive and a negative particle. You get some attraction from the Coulomb term, but the second term is effectively a QCD term. It's a strong interaction attraction. You can break it down into elastic and inelastic contributions to it, and that's shown in those two curves. But it's a positive, strong interaction, attractive potential.
Is it how that was calculated by?
This is done on the lattice. This is a lattice QCD calculation, a non-relativistic lattice QCD calculation. So not with quarks and gluons, but with baryons on the lattice.
In standard situation, this attraction appears as exchange of some Bose excitation. So that is standard how it appears in condensed matter.
Yes.
So can it be here characterized by the same idea or similar?
Well, it's difficult to say because the temperature is so much higher than what you see in a condensed matter system. So essentially what you use in a non-relativistic QCD calculation is a pion exchange on the lattice in order to get the attraction of the potential. So it almost turns into like a Yukawa type potential if you do it. So it is a pion interaction.
Yeah, but Yukawa is just the exchange by pi meson, so that he has obtained it in this way.
Yeah, so I'm not really sure whether you can at these temperatures make a connection to a condensation effect, the Bose-Einstein condensation exchange. I don't think so. The other question I forgot. I'm sorry.
Another question, you have shown a very nice picture of after oscillations, after merging of two neutron stars. My question is, what oscillates?
Oh, the ring down. It's the frequency of the gravitational wave. So I mean, this is a frequency spectrum of the wave that you have. So what changes in the gravity? I'm sorry, we get used to this. This is Any of those.
Yes,
Any
yes.
of those. Essentially, what you measure here is the T minus T mergers. So this is a frequency spectrum in milliseconds. And what essentially what hits you is a gravitational wave with a certain frequency. That frequency is changing. You have a different frequency in the in spiral compared to the post-merger effect. And that's really all you can measure from the gravitational wave. It comes in, it leaves a time spectrum, and that's it. I mean, it also leaves, and this is all simulation, so let's be careful, right? It leaves a time spectrum and an amplitude, but that's it. And then you can actually, and which is interesting when you talk about spin down and so on, you can relate it to measurements of the same effect, not the gravitational wave, but X-ray telescopes, gamma ray telescopes, then measuring other parts of the electromagnetic spectrum that can be related to that. And that gives you really some impact into spin down and things like that.
Okay, thank you.
Yes, yeah, so there's a gamma ray burst. I mean, there's many things that are related to that. I just wanted to show you what you can get out of the gravitational wave spectrum itself. There are other things that can be related to it. But I think nothing is as clean when it comes to the question of the core than being able to measure this ring down to very high accuracy. And we're about, you see this is a log plot, we're about an order of magnitude away from that. But that is achievable with new technology in 10 to 15 years from now. Let's not be too optimistic.
Okay, see you. I think you had your hand up. You want to ask your question? Oh, maybe you did. Okay. So if there are no other questions, maybe stop at this point. Let's thank Rene one more time.
Thank you very much. Thanks for hanging in for so long.